Chairman, and thanks the organizers for giving me this opportunity. And I'm really glad to see that we have set the stage for this discussion with the overall picture, and from there we moved on into the stress analysis and then got into the materials. So I'm going to delve a little bit more onto the materials, and that's where I'm coming from, the structural integrity assessment aspects. So you know why we do the structural integrity assessment and residual life prediction. So basically we look at failures and we want to avoid that, but in the process of doing that, the major inputs come from the viewpoint of geometry, and that's where I think the stress analysis and finite elements comes into the picture. And if the fits and tolerances change as a function of time, very often we have a good fit at the beginning of the introduction to the service, but after some time it kind of changes because of the stress distributions, plastic enclaves and whatnot. Then you will notice that the stress gets redistributed, so you're not going to evaluate for that. And many times the loading history is not the same as what we anticipated at the design time, so it changes. And environment, as what we understand from the previous speakers, is kind of changing from mild to harsh, and combination of hot and wet and corrosion and so on, and material degradation, which takes place amidst all these interactions, that gives you a combined effect of loading and environment, which is more synergistic, and as a consequence it kind of does not make a good sense to use the material property that has been estimated when the material was a pristine condition. And top it all, you will find very often we have the materials when it is in the fabricated condition, there will be locked in residual stresses and several other parameters that are there. So that is the reason why it is important to look at life prediction or life extension based on these things. From the viewpoint of what they use in the atomic power plants, at least the agency with whom I have been associated with, I know that they use what are called as surveillance coupons, where you will keep some of these pristine samples inside the hot cell, and as a function of time, as it ages, you pick it up and then try to evaluate the properties. So hopefully they expect that it will give you the right kind of properties, but unfortunately these pristine samples are held in the state of zero stress. As a consequence, the combination of stress and then the environment is also not experienced by that. So that's why we start looking at use of small specimen techniques to evaluate the material properties. And as what I see in the some of these points, during midlife updating also a small amount of material is extracted from the workpiece, and a small volume when you extract, you also need to know how to kind of get the properties correlated with what you do with the standard ASTM or British standard or Indian standard specimens. So this is where there is an importance. So if you look at this chart, which talks about the the methodology of life assessment, I'm sure many of us have this kind of plant information from the instrumentation, and from there we try to get the details about what the individual components are experiencing. So essentially through the transfer function analysis, we try to get to see what is a kind of individual component stress history, and then we break it up into the form of fatigue or creep, or in this case maybe even including the corrosion environment that you are going to look at. So we have two models, one which is looking at continuum, where you have the damage model, and then the other one is where you are looking at the crack model, where you assume that there is some kind of discontinuity and you want to look at that. So based on this, you notice that all this our fundamentals on fatigue or fracture or creep, all these things are being applied. But what is important to note is that the mechanical properties of the materials is the starting point for all these life predictions. And we all know that if I tell about ourselves as a humans, we will say that average life of human beings is say maybe about 60 years or 70 years, but then that's an average life. You have to also measure what is the individual's life. So that's the reason why the doctor says when you are past 50, go and do a full health checkup. And based on that, he says either you do an angio or whatever it is, and then later on he says you can have another 5 years of life or whatnot. So given that, now we have to move towards individual asset management, which means each equipment which has been manufactured in some fashion, is being put to use in some other location. So we need to know what is the property and how to use that to kind of arrive at the life of these components. So in this context, we use the material scooping methods, which have been kind of practiced by some of these companies like Rolls-Royce, and to some extent they don't allow us to kind of have access on them because they are proprietary. But then we know as Indians we have this Atmanirbhar and all those kind of schemes. We try to develop it on our own. So when you look at small specimen test techniques, a small volume is being used. How small is the volume? I can just show it to you in a while from now. See, this is the kind of a scooped region and then the scoop material. And from there, we are going to extract so many specimens. They are used for tensile tests and they are used for indirect property measurements like small punch test, or you use it for the Sharpie impact test and so on, and even fracture toughness experiments. So we make so many of these specimens from these, and what is important is to see how these results correlate with reference to the big size specimens that what we use in the ASTM standards. So this is where we start looking at what is the effect of size scaling of these samples, because these allow us to go to the in situ and extract the samples and use it for the future life predictions. So if you look at what the ASTM subcommittee E1002 on behavior and use of nuclear structural materials, they have summarized the different kind of tests and which are all the laboratories that are working on it. And what caught my attention as a fatigue and fracture person is that not too many have worked in the areas of fatigue. So that's the reason why I started pinning my effort onto this. And I don't want to get into too much of details. I'll just show you a few of the results. But then what we did over the last 15 or 20 years is to work in the small volume specimens to test the tensile properties and the fatigue properties. We looked at the miniature tensile samples. Then we use the indirect method, which is called as a ball indentation testing, both for static indentation and fatigue properties. We did for the small punch testing, because the state of stress is changing depending on the test methods. You will have a uniaxial or a biaxial or a triaxial state of stress. So this is all that we did, and then we did multi-sensor techniques to identify failure in miniature specimens. To give you a glimpse of the results, you can see here. We have done the fatigue life curves obtained through the cyclic ball indentation, where you can see that the base metal is shown over here, and you will also see that the data for a welded region, different kinds of weldments, how it changes. So which means that if I have this data, I can go and correct. If supposing I have a welded region where I want to predict the failure, I'll use appropriate strain life curves rather than having to use the pristine material data. And when we did with the multi-sensors technique, we try to correlate the data of fatigue life from various test methods, and the table what you can see over here shows that there is a good comparison. We have tried the acoustic emission technique. We have also used the hysteresis area for measurement of the the energy that is stored during the fatigue cycling. So this is one of those tables. And you can see here when we did a small scoop sample and I do a cyclic small punch test, I'm able to get the kind of different micrographs, which also suggests where the crack is initiating, how it is growing, all that kind of a detail. And apart from that, we also did some crack growth studies using the miniature samples, where you can see in the graph on the right hand side the data from miniature samples, like as small as what you see in this left, this 15 mm by 5 mm by 0.5 mm thickness, and the data compared with what you get with a standard specimen. So these are the the other work that we are looking at. So from an academic perspective, what we are looking forward is that effect of stress state on the failure response, whether it's a tensile or fatigue, or you are looking at uniaxial, biaxial or triaxial. And we also want to look at high temperature fatigue property estimation using small specimen test techniques. I mean, from the gathering over here, from what I see, you are more worried about maybe less than 500 degrees centigrade kind of operating conditions, but there are some power plants where they are now looking for even going to higher temperatures. So we need to look at the fatigue properties using the small specimen test techniques. And creep and fatigue interactions, they become very important when we talk about some of these power equipment. And thermal and mechanical fatigue, that becomes another important aspects. And then, as what my previous speaker was talking about, the effect of corrosion and fatigue, how do I kind of couple them? So that becomes important to study using the small specimen test techniques. So we have to also look at small specimen test techniques for new materials like additively manufactured or engineered materials. So that's kind of other area that we are focusing on. So with these kind of glimpse, I would probably stop my talk. Hello for more questions and interactions. Thank you.
I think that was pretty much on time.